Unit 5A, Lesson 3. In this lesson, we're going to discuss more theorems related to circles. These theorems are going to focus more on the segments created within and outside the circle. The first example we're going to go through is going to involve Theorem 10.4. So we can see we have points along the circle R, P, and Q, and the center of the circle is O. We have two arcs that are formed. We have arc PQ, which is 115 degrees, and arc RQ, which is also 115 degrees. We have the chord QP, which is 12 units, and we have the chord QR, which is length X. That's what we're trying to find. So what this theorem tells us is if we have two minor arcs that are the same length, the same measure, then the chords that intercept those arcs must be congruent. So we know the measure of arc PQ is 115 degrees, the measure of arc RQ is 115 degrees. Since those are congruent, if we know the length of chord PQ is 12 units, then the length of X must also be 12 units. In this next example, we're going to use Theorem 10.5. So we have two chords intersecting inside the circle. We have chord AC and chord BD. We know that chord BD is going to be the diameter to the circle because it goes through the center. We know the length of EC is 12 units. We're trying to find the length of segment AE. So what this theorem tells us is if we have a diameter to the circle intersecting another chord such that those two chords are perpendicular to each other, then the diameter bisects the other chord. So we can see the diameter BD is perpendicular to chord AC, so chord AC must be bisected. That means if the length of EC is 12 units, the length of AE must also be 12 units. In this example, we're going to use Theorem 10.15. So we have two chords intersecting in the circle. We have chord PR and chord QS. This theorem tells us that if we take the product of the segments of one chord, that is going to be equal to the product of the segments of the other chord. So we can take 8 times 18 and set that equal to y times, this is going to be a length of y as well because we can see those two segments are congruent to each other. So y times y is y squared. Now we just have to go through, use algebra to solve for y. 8 times 18 is going to be 144 equal to y squared. Now to get y by itself, we would take the square root of each side, and we get y is equal to 12. Technically, we would get plus or minus 12, but we're talking about a distance, so we only have to take the positive value. The last example we're going to go through is going to involve a tangent segment intersecting a secant segment outside the circle. This is going to involve Theorem 10.17. We would use a similar approach if we had two secant segments intersecting outside the circle. That would just be Theorem 10.16. So what this theorem tells us is that we can take the length of our tangent segment, which is x, and multiply that by itself. So we would get x squared. Set that equal to the length of our external secant segment, which is 3 units, multiplied by the length of our entire secant segment. So we would take 3 plus 9. The length of this entire secant segment, BD, is 12 units. Now we just go through, simplify to solve for x. X squared is equal to 3 times 12 is 36. We would take the square root of each side of our equation and get x is equal to 6. Again, technically we would have plus or minus 6, but we're talking about the length of a segment, so we're only going to take the positive value.